Okay, start recording. Well, in the last lecture we discussed the transformers. We discussed the transformers. We discussed ideal transformer and real transformer with finite permeability of the core. Well, today we will discuss the real transformer with finite permeability and flux leakage. It means, okay, the magnetic permeability of the core is finite, as we discussed in the last lecture, and also we have flux leakage, which is the real case in most transformers. Okay, the real transformer is finite permeability and flux leakage. Okay. In the previous lecture we discussed the ideal transformer and real transformer, and in both cases we assumed that all flux produced by a coil is contained within the core. It means no flux, no magnetic flux outside of the core. Well, this is not always true. This is not always true, and there are the conditions under which some of the flux closes outside the core, or there is no core, or there is type of transformers where there is no core, without core, or such kind of transformers you may know are called air transformers. Okay, in the case, let's consider two coils in the air. So sorry, let me move. Two coils in the air. This is also the type of transformer where there is no core. Well, in this case, we don't know how much of the flux connects two coils. Well, the magnetic flux produced by the first coil, for example, some part of the magnetic flux connects these two coils, but the other part of the magnetic flux flows out to the out of the core and closes somewhere here in the air. It means does not link second coil with the first coil. Only okay, some part of magnetic flux links two coils, and but we can assume that a fraction of the flux produced by one coil links the second coil. Here, okay, I denoted it with green lines. Okay, some part or some fraction of the total flux links two coils. Okay, we suppose that this fraction is K. This fraction we call by K. Well, because of that, the mutual inductances also change by this fraction. That is, if all flux links both coils, the the inductances. Okay, the mutual inductances of these two coils will also change by this fraction, by fraction k. In the previous section, we said that we have seen that all the flux links two coils, and the fraction of mutual we didn't care about the fraction of mutual inductances. But in this case, we have some, in order to compute the mutual inductance, we need to take into account only the fraction of that mutual mutual inductances. So if only fraction k links coil 1 and coil 2, what we have? Okay, self inductance, of course, doesn't change. Self inductance L11, we have seen mu s over L multiplied by n1 square, as well as self inductance of the second coil, mu s over L multiplied by n2 squared. And now, okay, let me scale this down and put it here. Now the mutual inductance is L12, will be equal to the mutual inductance of L21. Okay, it is obvious, and will be equal to, in previous section we said that mutual inductance of two coils is mu s over L n1 and 2, but in this case, in the case where we have flux leakage, we said only the fraction k links two coils. That's why we put here the fraction k. Sorry. Okay. So, okay, and let's take the product of these mutual inductances. The product of these self-inductances, L11 multiplied by L22 is equal to, so mu s over L, mu s over L squared, n1 squared and 2 squared. And okay, let me scale down this as well. Okay, and from this we can write the square root of L11. From this we can write square root of L11 multiplied by L22 is equal to mu s over L and 1 and 2. Okay, this you can You can see this expression is the expression for mutual inductance that we have seen for the ideal transformer. Okay. So, and we have if we take this and put here, we have what we have. So L1 2 equal L2 1, which is equal to K. Okay, instead of mu s over L n1 and 2, I put square root of L1 L2. Square root of L1 1 L2 2. Okay, and the electric motive force in the so note that this is first coil, this is primary coil, this is secondary coil, and electric motive force in each coil so electric motive force according to the Faraday law is dF dphi over di, or in our case the self-inductance, electromotive force due to the self-inductance minus electromotive force due to the mutual inductance, or namely we can write L11 di1 over dt minus, and the expression for mutual inductance we found as K square root of L11 L22 multiplied by d I2 over the t, and so electric motive force in the secondary coil is equal to, so this is kind of vice versa, L11 L22 di2 over dt minus L22 d sorry, here di1, this is 1 di2 over the t. Okay, this these two are the these two are the equations to find the electric motive force in real transformer with some flux leakage. And here okay, we said K is coupling coefficient and the k usually not usually k is always greater than 0 and less than 1. Okay, these two are the equations for real transformer with finite permeability and flux leakage. Okay, so let's see some examples of application of transformers. First example is the toroidal transformer. So okay, this is the page 538. Application of toroidal transformers. So let's read. The toroidal transformer, a widely used transformer in high quality audio and test equipment, is built around a toroid core. So this is you can see the toroidal core. The transformer shown is designed to supply 48 volt at 2 ampere for the output stage of an amplifier. So here for the output, the voltage or EMF, electromotive force, is 48 volt and the current supplied should be 2 ampere. So the toroidal core has a cross-section area of 400 millimeters squared, a mean magnetic path of L equal to 200 millimeters, and the relative permeability of the core is infinite. So the permeability now in our case is infinite, and this transformer we can assume as an ideal transformer. The primary core operates at 240 volt, so 240. Here there's an mistake. This is not 24 but this is 240. If you want 240 volt, the primary core operates at 240 volt and 60 hertz. If the primary coil must have 800 turns to generate the required flux in the core, calculate the number of turns in the secondary and current in the primary. Show that the result in A remains unchanged if the permeability of the core is finite, as long as all flux remains contained within the core. So let's first switch to the question A. From the problem, we know that we can assume our transformer as an ideal transformer because the permeability of our core is infinite, and for the for the ideal transformer, we have the ratios which says V1 over V2 equals 2 N1 over N2. From this ratio we can clearly find N2, which is from this ratio N2 is equal to N, this goes here, N1, N1 multiplied by V2 over V1. So we know the numeric values of let me write here. So we know the numeric values for N1, V2 and V1. So we are told that primary core must have 800 turns. So N1 is 800 multiplied. The output voltage should be 48 volt. 48 volt over the input voltage is 240 volt. Okay, from here we can simply find that number of turns in the secondary coil should be 160 turns. So if we switch to the next part of our question, so second part of the question A says, so we found the number of turns and current in the primary, so we also have to find the current in the primary core. Again, from the equations of ideal transformer, I1 over I2 equals 2 N2 over N1. over N1, and from here we can find I1, the current in the primary core, will be equal to I2 N2 over N1. So the answer is okay. The answer is I2. I2 is 2 ampere multiplied, and 2 we found 160 turns. Multiplied by N1. N1 is 800 turns. Okay, so what we have here, this and this simplifies by 5, and 2 over 5 gives us 0.4. 0.4 ampere. Okay, we found I1, which is 0.4 ampere. Okay, the next part of our question, part B. Show that the result in A remains unchanged if the permeability of the core is finite, as long as all flux remains contained within the core. So in the second question, we assume that our transformer is real transformer with finite permeability, and we assume that all flux remains within the core. It means that, okay, for a real transformer with finite permeability, we have the relationships. Okay, electric motive force 1 for the real transformer, EMF 1, was equal to mu s over L and 1 squared d I1 over dt minus mu s over L and 1 and 2 d I2 over dt. So okay, let me scale down this and put it here. And the electric motive force in the secondary circuit for the real transformer was electric motive force in the secondary circuit equals to mu s over L and 1 and 2 di 1 over dt minus mu s over L and 2 squared di 2 over dt. So okay, now let's take the ratio between electric motive force 1 and electric motive force 2. So electric motive force 1 over electric motive force 2. This will be equal to let me write in the new page. So first let me copy this part. Okay. Okay, so copy and paste it here. So let's take the ratio between electric motive force 1 and 2. If we take the ratio, one over electric motive force 2, what we have? We have so we have here I look here I take n1 and here one of the n1 out of the bracket, n1 out of the bracket, n1 out of the bracket, and here vice versa, n2 out of the bracket and one of n2 here out of the bracket. So what we have in this case, n1 mu s over L n1 di1 over dt minus mu s over L n2 di2 over dt over n2. What we have here, mu s over L n1 di1 over dt minus mu s over L n2 di2 over dt. So as you can see clearly, this and this simplify each other, and what we have everything equals to n1 over n2, which is exactly the ratio which we wrote for the ideal transformer with infinite permeability of the core. So electric motive force 1 over electric motive force 2 will be equal to n1 over n1 over n2. So what we learn from here, because of n1 multiplied I1 equals to n2 multiplied I2, and since I2 produces a flux which opposes the flux due to the I1, the net flux in the core will be 0, and this and if we assume that net flux is 0 and there is no flux leakage, we can again assume the transformer as an ideal transformer. And second thing is, because of that this is the ideal transformer, as you have seen from the problem. The dimension of the core and the frequency of the source are not so important. They do not figure in the calculations. So here here in these calculations you don't see anything about the frequency of the source, or the anything about the dimensions of the core, as well as here you don't have you don't have any relationship of dimensions, of the dimensions and the parameters of transformer. But in practical transformers, the dimensions define the maximum flux density allowable without the core reaching the saturation. Well, this you will see in further in your practice. Okay, and one more notation: the toroidal transformers are very good in very good in audio applications, because they are low leakage transformers. The flux leakage from the core is very low, and typically they offer the shortest magnetic path, and therefore the lowest reluctance, in addition to being an economical in both winding and core materials. Okay, further material you can read from the book. Let's switch to the next problem. So the next problem is this one. Okay, let's put it here. So a high frequency transformer is made in the form of two coils on a non-magnetic form, which means permeability of the core is mu 0. It means there is, you can assume that there is no core and there is only air between two coils. It is okay. It is illustrated in the figure 10.15. The self-inductance of the coil 1 is 10 millihenry, and of the coil 2 is 20 millihenry. The current in the primary is I0 sine omega t, where the frequency is 1 megahertz and I0 equal to 0.1 ampere. And the secondary coil is open. The coupling coefficient between two coils is 0.2. So K is K is 0.2. So we need to calculate the voltage required in the primary to sustain the given current. Okay, and the voltage in the secondary circuit and the secondary coil. So as you have as you can see, this transformer must be treated as real transformer with 80% of flux leaking out and only 20% of flux links to coils. This K equal to 0.2 is saying about this. And in addition, as the secondary coil is open, as the secondary coil is open, current in the secondary coil is 0. Okay. Well, we need to use the equations for. Okay, we need to use these equations for real transformers with flux leakage. Okay, I2 is 0. Okay, let's switch to this. Electric motive force 1 is equal L. So let me, we have 2 more minutes. Okay, let me copy this. So copy, and I put it here, paste, I'll move it here. Okay, now we said that as the as the secondary coil is open, I2 is 0, so this part simplifies because of I2 0, this part is 0, as well as this part also becomes 0. So now let's write the electric motive force 1. Electric motive force 1 equals to, okay, we are running out of the time. Let's reconnect again. I will pause, resume recording, and let's go back to our sketchbook. So from the first equation we can write the expression for electric motive force 1, which is equal to L11 di1 over the T. So self-inductance of the primary coil is given is equal to 10 millihenry, which is 10 microhenry, sorry, microhenry, which is 10 to minus 5 Henry, and I1 is given as I0 sine omega t, is given as sine omega t, where f is equal 1 megahertz. Okay, first of all, let me write I1, which is equal to I0 sine omega t. Okay, here we know the sorry, let me write in red. I1 equals to, it is given as I0 sine omega t. So from the problem we know the value for I0, which is 0.1 ampere, and we don't know omega, but we know the frequency f. We know frequency f, which is 1 megahertz, and if we know the frequency f, we can find the frequency. We can find as well omega as well, which is 2pf, and it will be equal to 6.28 10 to the 6 radians per second. So okay, let me scale down all this in order to write everything in one page. Okay, and let's move it. Okay, let's move it somewhere here. Okay, now let's write again electric motive force 1. L11 is 10 to minus 5, 10 to minus 5, and I1 is, we said I1 is 0.1 sine omega t, and if we take the derivative from I1 with respect to time, we get omega multiplied by I0 multiplied by cosine omega t, and which is equal to 10 to minus 5 multiplied omega we found as 6.28 10 to 6. I0 is given as 0.1 cosine omega t. Okay, this is 10 to the power minus 5, this is 10 to 6, and this is 10 to minus 1. Everything simplifies because this is minus 1, this is minus 5, this is minus 1, and this is plus 6. Everything simplifies. Now we have the expression for electric motive force 1. Electric motive force 1, which is equal to 6.28 cosine omega t volt, where omega is equal to this value. Okay, we have done the first part of our question, the voltage electric motive force required in the primary to sustain the given current. Okay, we have found electric motive force in the primary coil. Now we need to find electric motive force in the secondary coil. So this is the electric motive force in the primary. Is equal to 6.28 cosine omega t. Okay, electric motive force in the secondary coil is given by by this expression, again, where this part equals to 0, because I2 is 0, and let's write electric motive force 2. Again, let me copy this and paste in a new page. Copy. So paste here. Okay. Okay, electric motive force 2 equals, so electric motive force 2 equals to K, which is given, L1, L2, which are also given, self-inductance of the first coil and self-inductance of the second coil, and the derivative of I1 with respect to time. We have also computed this derivative, which was equal to omega I0 cosine omega t. Yep. Yeah. Yes. Okay. Now the electric motive force 2 is simply K is given, coupling coefficient is given as 0.2 multiplied square root of 10 microhenry multiplied 20 microhenry. So 10 microhenry is 10 to the minus 5 multiplied 20 microhenry is 20 multiplied 10 to the minus 6 multiplied by di1 over dt, which is omega I0 cosine omega t. Okay, omega was equal to 6.28 10 to the 6 multiplied I0 was equal to, if I'm not mistaken, I0 was 0.1. Okay, 0.1. So 0.1 multiplied by cosine. Okay, we are out of space. Let me scale it down a little bit. Let's move here. Multiplied by cosine omega t, where omega is 6.28 10 to the 6. Okay, if we compute this, what we have, so let us take the calculator. So 0.2 multiplied by 6.28 multiplied by 0.1, 0.2, 0.1, 6.28. Okay, we have, so far we have 0.1258 10 to 6, and let's compute the square root. So 10 multiplied by 20 multiplied by 20 is 200, and square root of 200 is 14.14 14.14 10 to the minus 6 multiplied cosine omega t. Omega is 2 pi or 6 0.28 10 to the 6 t, and is equal to 14.14 multiplied by 0.1258 is equal to the electric motive force in the secondary coil equal to 1.78 1.78 multiplied by cosine 628 10 to 6 t. So this is the electric motive force in the secondary coil. Well, we are asked to find the voltage in the secondary coil. Okay. Volts, of course. So we have found electric motive force 1 and electric motive force 2. Okay, now let's have a rest for 5 minutes, and after that we continue our lesson.